Hello, good morning.
Good morning.
Good morning.
Good morning, everyone. Yeah, so I think we're going to start right now. Let me just share my screen. Okay, so today I would like to just discuss a few things. One discussion is going to be on the design of gear trains and gear systems, and which is the last part of the class. And then another is going to be on review of a final exam that I gave in the fall of 2014 to give an idea about the level of complexity or requirements in the final. So if you can see here, the design of gear reducers or gearboxes in general involves sizing of the gearbox, determination of the number of gears and the number of teeth on each gear, determination of the forces that are transmitted in between gears, both tangential and radial, determination of the reactions and the supporting shafts, determination of the fatigue life of the shafts, and then finally determination of the deflection. So this is kind of the sequence of events that need to be considered when we look at design of gear systems. So in this example here, which is a case study, we have a gear reducer box to reduce the the input speed from 1750 RPM to a required output speed and range of 82 to 88 RPM. So there's a reduction ratio here that needs to be considered. And we want to just kind of to see what I'm not going to review every little detail, but just give an overview of the main steps. So we want to transmit. So we figured out the ratio of the reduction from 1750 to, let's say, 85. So we can divide these two numbers and get a reduction ratio. And this reduction ratio, if it is greater than 100, then we have to consider multiple gears to reach this reduction ratio. If it is less than 100, then we can achieve it with only 2 steps, which is the case here. So that's, first thing. And then we have some kind of constraint on the size of the gearbox. So if the gearbox is, say, to be 22 inches high, then we should be able to kind of put in gears inside that would fit. If we decided that we have to have 4 gears in this case, because the reduction ratio is less than 100, then we would be able to determine what is the sizes from the requirement of the size of the gearbox. So this has nothing to do with the input velocity or input speed or the input horsepower. It's just sizing. So the way it works is that for the sizing, I'll show you the sizing first. And once we did the sizing, we say, gear 2 is going to have so many teeth, and it will have a pitch of so much, and it will have a diameter of so much. So we selected basically the gear. We can go ahead and order it online. Then we wanted to figure out, what kind of forces will be on that gear, or if we order from online, would it actually take these forces or break apart? So that second step has nothing to do with sizing. It has something to do with the horsepower. If it is very high horsepower, then it's going to be a lot of forces. If small horsepower, it'll be small forces. So here is 20 horsepower. So the horsepower is the product of it's power. So it's a product of the force times the velocity in some sense. So that's how you think about it, some conversion factors. And therefore, if we have the velocity related to the RPM, we determined that already, then we can figure out the forces. And that's it. So horsepower means first sizing, and that sizing gives us the diameters and so forth. And then the RPM and the diameter gives us some kind of a velocity, tangential velocity, and horsepower will then give us forces, and then the forces will determine everything else about the strength of the material, if the gears are going to take that force, the contact pressure, the forces on the shaft, the deflections, and everything else, the rest of the story. So this is kind of a summary. So if I just walk you through that, if I look here, the reduction ratio is 1/20. So we need to reduce it by a factor of 20. And therefore, if it is reduced, it's a reduction a reduction process. Then the input shaft, the input gear has to spin a lot faster than the output gear. And the only way it can do that if the input is smaller than the output. So it spins a lot, and then the output spins slowly by a factor of 20. And that you reduce it 2 steps, so N2/N3, N4/N5. So you have some uncertainty what to do about this ratio, how to split it. The way that is recommended in design, you can split, of course, arbitrarily, but from a design perspective, the optimal way is to split it evenly. And evenly, just you can take the square root of the ratio and then use it to split each stage. So stage 1 is 1/4.5, and stage 2, 1/4.5. Now, there's another problem, is that you cannot really select gears that have fractional number of teeth. So this is one limitation. The other limitation is that if we select gears that have a very small number of teeth, then they can lead to interference between the gear teeth. So there is a minimum number that corresponds to each pressure angle. For the modern gears, the pressure angle is 20 degrees, so the minimum number of teeth is roughly 16. You have a formula for it, but if you work it out, it becomes 16. So you can use this as a constraint for the smaller teeth, the gears, N2 and N4. And from that, you can up it with the reduction ratio, with the ratio 4.5. You get 72.64. Obviously, that's not going to be a good choice, so you have to approximate it to the next level up or down, so 72 here, and therefore you can get an acceptable output RPM. So we've done now with the teeth. We've determined the number of teeth and the input RPM, output RPM, and how it splits. Then to figure the size, to order the gears, go ahead and order the gears. The number of teeth is not sufficient, so we need to have the pitch, because the pitch determines the diameter of the gear, because you can have the same number of small size gear or large size gear. So the pitch is important. And the pitch, the only way we can figure it out is how big the gearbox is. If the gearbox is very small, like for a clock, then they have to be very tiny gears. If the gearbox is big for a car, then the pitch is going to be large. And therefore, we must be given what is the size of the gearbox. Here, the size is given to be 22 inches high. So if that you split the 22 inches high, like you can see here. Y is 22. Then Y, it must be equal to D3, the entire diameter from here to here, plus D2 over 2. So you go from this point up to here, and then you go up to D5, and then you take another D5 over 2, and then you must have some space between D5 and the clearance to the upper wall of the gearbox, and then you add the thickness, and you know now all of the diameters are equal to the number of teeth divided by the pitch, because the pitch is a diametral pitch, capital P, which is a little bit different from the lowercase p, the circular pitch. Circular pitch is like the inverse of the diametral pitch. It's inches per tooth. The diametral pitch is number of teeth per inch. So you work that out and you determine the pitch, and that's it. So now we have the pitch and number of teeth, then we can go ahead and select the gears and order these. Yeah, so in this equation, you find that the pitch minimum is 5.76 teeth per inch, and therefore all the gears will fit in the box and will transmit. Now the next question is that will that really transmit 20 horsepower? What if I make it 400 horsepower? Would that work? Well, it may not work, because 20 horsepower is related to how strong the gears are, not related to how big they are. So that comes the question of lifetime at that point, and the lifetime depends on the forces. So if we go back, we see here that our next step is actually to get into the torque business. Then the horsepower is the torque times the angular speed, and which you can convert to RPM with a conversion factor, and that we can use to determine forces. So T is H is constant. If you have an efficiency because you lose some of the horsepower in friction and in irreversible heat loss and so forth. So there's usually an efficiency of, say, 0.75, 0.8. So that needs to be determined from measurements, usually measurements or experience. But here there's no efficiency given, so it is assumed to be 100%. So the input horsepower is the same as the output horsepower, which is the product of the torque times the RPM with the conversion factor here. So you have to kind of worry about these conversions. And then that we can solve now for the torques on the input gear T2, on the intermediate gear T3, and on the output gear T5. So if you look at the torques, the intermediate gear has 270, but the output gear, because it is we have like a big reduction in the speed from 1750 to 86, then the big reduction in speed will have to be associated with the output being like a large gear. So it has 72 teeth. So it's a large gear. So the large gear will have the highest torque that's acting on it, which is what you want here. Otherwise, it will break. So that kind of gives you an idea. These are the torques, and the torques will, to a very great extent, determine whether the gears are going to survive or not. If they're going to be, if you can select them from plastic, from titanium, from steel. We have some limited selections, obviously, that is determined by the strength of the material. So the next step is from the pitch, now we know the pitch, we obtain the corresponding diameters of the gears, and we usually at that point, after we sized and we obtained the RPM for each one of the stages. Then we just say that there's a tangential velocity. The tangential velocity is R times omega, right? So V is equal to R omega. But then with the conversion of the units, if you have, foot, usually they like in practice, they like this velocity to be in foot per second. So you convert inch to foot, you get the factor of 12. And then you have now the what's called the pitch line velocities. So each gear, like each contact, there's a velocity at the interface that is called the pitch line velocity that is determined here. So we have these pitch line velocities. And the pitch line velocity now, the velocity times the force at the contact, because you can imagine like the two gears are contacting, there's a velocity, and the velocity times the force is equal to the horsepower. So the force V23, for example, times the velocity V23 times the force, tangential force in this case, because it has to be along the pressure angle, along the tangent, is equal to the horsepower times the conversion factor. So from knowing the pitch line velocities and knowing the horsepower, that determines the contact forces. These are tangential ones. And once we know the tangential contact velocities, we use the pressure angle to determine a radial component and a tangential component. So, so let me skip that and then go directly to the. Okay, so this is the selection of the gear. So the gearbox looks like this: is an input shaft, and the output shaft is in line. So that's a design requirement. So the center line for input is the same as the output, and that also puts a constraint on the size of the gear 2 plus gear 3 should be equal to gear 4 plus gear 5. That I'm talking about diameters here. So that's kind of requirement that helps us in the sizing. And then when we look now at the tangential forces that we obtained, we can determine radial components by taking the tangent of these forces. And therefore we have both radial and tangential components of the force. And those give us the balance of the forces on the system. So if you look here, you have here, let's say we're going to take one of the two shafts because the gearbox has two shafts. So if we take the shaft that contains gear 2 and gear 5, then gear 2 has a force that is decomposed into a radial 2-on-3 and a tangential 2-on-3. And gear 5 has also a radial 5-on-4 and a tangential 5-on-4. And we learned in the class how if we take the system, these are two planes that are perpendicular, and on each plane we can do the statics independently. And the statics, meaning that what are the forces on the reactions. Luckily, we don't have any indeterminate systems, so it's all determinate, very easy. So you take the moments about this point, the moments this point, and then you have vertical, horizontal equilibrium. You get the 4 reactions at the two ends at A and B. And then the next job is to construct the torque diagram. So the torque diagram at this center, like you can see G here as the center of the gear, there was no torque, and at that center we have a concentrated torque. So assuming that the torque in between the gears is concentrated, so it's a jump in the torque value to 3240. And then since there's no forces acting between G and J, then the torque remains constant. And at J, then we have a torque that is opposite and equal in magnitude, and then it goes to zero, because that's kind of equilibrium. So this is a torque diagram. So if we're designing for torque, the torque is constant, continuous. In other words, it's not fluctuating, doesn't change. So it gives you, once we have the torque, it gives you stresses on the shaft, and the stress system is shear. So you have a shear on the shaft that is fixed. It doesn't change with time. So we can deal with this as the mean stress when it comes to fatigue analysis. So set this on the side, and then we go ahead and do a shear force diagram for the XZ plane, as you can see here, from the forces. And these are all point forces, so it's a very nice, easy system. There's no distributed force, uniform or linear ramp or whatever. We just have point forces. So the shear force diagram is jump, constant, jump down, constant, until you hit zero again. The moment diagram is the integration of this. So the constants become linear, and we don't really calculate many points, only at the critical points. We just take the moments to determine the coordinates of this point and this point. I'm going fast because I know that you guys know this stuff. You did very well on the midterm, but I'm just doing it as a general review. So here is the XZ plane. The XY plane is also done similarly. Now the point is that when we do the analysis for stresses, we don't care about the independent individual components. We want to find the resultants for everything. The resultant for torque is the same one, is the torque, same torque. Resultant for moment, then we have a moment on the XZ plane and a moment on the XY plane that must be combined as vectors. So we don't know where is that vector maximum, magnitude of that vector maximum. So the best way is to just do it at maybe one or two critical points. And the critical points will be at the shoulder here or the shoulder here. Well, if this shoulder here, this is a fat section of the shaft, so it might be on that side and on this side when the shaft is reduced in diameter. So that's what we do here to find the combined or the vector sum of the two moments. And from the moments, we have now a moment and a torque. So the moment is alternating because the fibers on the shaft that on the positive and the tension in one part of the cycle will reverse and become under compression in the other part. And that's why we think of the moment as an alternating component of the stress. And it's the nature of the stress that results is a tensile or compressive stress. So it's a uniaxial stress. While for the torque, the nature of the stress is shear. So when we do failure theory, when we combine them to get something equivalent, we use von Mises, for example, would be the square root of the sigma axial square plus 3 times the shear square. So it's a simple stress system. It doesn't have many components, only one axial, one shear. So you can use von Mises or equivalently distortion energy theory, and you can do all of your fatigue analysis and all of your failure criteria based on that. So I think this is kind of here. I will leave the rest here for you to look at. There's a whole bunch of equations that are empirical, and these are, we have to accept them because that's a design course. So there's no, like, we don't really go into derivations of these equations. A lot of them are from experience and empirical. For example, the ones that we use in fatigue is to have a relationship between the ultimate strength of the material and the endurance limit. Okay, so how does it come about? The ultimate strength times a factor gives us endurance limit in the laboratory. So this factor is, let's say, half. So you go from 100 KSI to 50. Now, this SE in the laboratory, how does it translate to an SE for the shaft? There's about 5 factors that must be considered: size factor, load factor, temperature factor, etc. And these are all, we have empirical relationships, but the bottom line is that you reduce from 50 to something smaller, maybe 30 or 35, and that is the one that you design your shaft for. And you get, a diameter that can satisfy that based on the distortion energy criteria. The other aspect of the design is the design of gears themselves, and the gears is some Lewis formula that I have in the lecture notes, and this can determine, it's based on bending, simple bending, with some additional factors, also the wear of the gears that must be taken into account. And that we can, just determine whether the gears themselves are strong enough to actually take these contact forces, or we should modify them to change them. Now, if it turned out to be that they need to be modified, one simple solution is to change the face length of the tooth, because the tooth, if it is skinny, then it takes small force. And if the force is too high for it, then you can extend it longer. Of course, you cannot make it very long, otherwise the gear we cannot find it. So there's kind of a limit on the face length that need to be considered. All right, so the overall, now this is a case study. It is, you cannot do, and then you have deflection. We'll talk about deflection. Deflection, we do the deflection calculations. We used analytical solutions, integration of the deflection equation, 4 times. It's a 4th derivative equation from the forces, and then we integrate it to get the deflection. But in reality, when you have various thicknesses for the shaft, that is done numerically, and I have a computer program that you could use to do that in design calculations. And there are limits on both the deflection and the slope, design limits on the deflection and the slope that must be satisfied. So if you look at this totality of the case study, you see that it can be done. Like we had it in one of the classes where they were required actually to machine and assemble and test the gear reducer assembly, similar to this type of problem with some other variations on it. And at UCLA, of course, the students have the access to the machine shop and worked in teams, and they actually demonstrated it for noise and for vibration. And the design basis is exactly what I was describing here. And, as if you go to the real life, you'll see that such a design procedure is very powerful, even though it has some empirical equations, some things like that, but it allows you to actually do a very realistic design for any machinery in which you want to transmit power, from one axis to another. In typical exam, of course, if we have a comprehensive question, for example, in the MS, that could be a type of question with a variant on that. So you have maybe non-intersecting shafts, you have shafts at 90 degrees, you have other constraints, but the general procedure is similar, and it means that it's a long problem, and it can require several hours of design iterations. Maybe using MATLAB would be the easiest way, but it is usually done, let's say, in about 24-hour question for comprehensive. On the final exam, we don't do that. So we just, take bits and pieces to try to study those as we did in class, because the objective was really to allow us to do a comprehensive design. But for the exam, we take bits and pieces. So unless, if you have questions, I can entertain any questions right here. And then I would be able to go to the to a final, to review the one final exam.
I have a quick question about for the final.
Yeah.
Can we bring our own notes as well as the book, or is it solely just the book?
Yes, yes, you can bring in your notes as well as the book. There's no problem with that, because the final can see a lot of we've gone over many design procedures, and a lot of them are in the book, and many graphs, and that's the real life. You know, when you work in your work, you're not going to be relying on your memory for these equations, but you rely on your speed and knowledge of how to use them in the most efficient way. So your notes will be fine.
Okay, thank you.
Yeah. Any other questions?
None here.
Hello? Okay, so now the final, I think, is it's next Saturday, right? Yeah.
Yeah.
That's correct.
Yeah, the final is next Saturday from 1 to 4. I sent the notes, and this is a final that was given in fall 2014. So I just want to go over some of the questions to give you a feel of the level of problems, or the focus at the end. All right. So it says here it's a book exam with no additional material, but we discussed it that your notes are okay. Electronic version, some people have electronic version. It's all right to use your laptop, but of course, if it is proctored, we check the laptop, so make sure that you don't have the solutions there, and solution manual prohibited, and exam is 3 hours. So speed is interesting. So if you look at the first problem, it's a beam stress problem. It's a typical problem. And beam stress problem, to design a beam, we need to know force system. Like you have a concentrated force on one end, 2,500 pound force. You have a distributed load, 400 pound per inch. You have supports. In this case, they are simple supports. No, we don't have the constraints, additional constraints. Otherwise, it will take longer time to solve. So simple support, and you will have a cross section. So the cross section cannot be crazy. So it has to be something like this, or an I-beam, or a box, or something that in which you can calculate the area, and you can calculate the second moment of area, the I. So it's no problem. And the force system is simple. Why? Because you can calculate the reactions. You can calculate the moment distribution on the beam. Once we have the moment and the area properties, then we figure out where's the maximum moment. The maximum moment, we may have to do it by inspection if we are smart enough to find it, or if we're not, then we just take the derivative and find where this maximum moment is, and then we design. So design meaning we calculate the stress at the tip here, and the stress at the tip down here. That's a tensile and compressive stress. But that's not sufficient, because we have to consider also the vertical shear. And the vertical shear, V, can produce a shear stress on each section. The shear stress is 0 at the top, 0 at the bottom, but it kind of builds up, and it might actually give you something kind of to worry about at that interface. So the idea here is the bending type stresses are easy, but the shear stress has to be evaluated, and then when you combine them to do a design factor of safety, then you use like a von Mises type combination, or some other, depends on the theory. But so this is the first step is statics. So I hope that everybody can do the statics easy, because if you mess it up, then kind of it looks bad throughout. Like I cannot do much about it when you get bad numbers. It's gonna it cascades through. Although I give like partial points, but it cascades through still. So if you do the statics well, you get the reactions, and then you get the shear force, and this is a shear force diagram, and the bending moment diagram is linear. And we have sections here from A to B. So I didn't do it fancy with the singularity functions, but just section by section from A to B, and then from B to C. So from A to B, you have a V and an M. From B to C, you have a V and an M with equations. And then you take the derivative of the moment, you get the position where you have maximum moment, and you find the maximum moment. And then you calculate the properties of the area, the center, centroid of the mass, the moment of area of the top piece and the bottom piece, combine them, and use parallel axis theorem to get the total. So that has to be kind of like second nature now. So now we can go ahead and find the maximum tensile and compressive stress at the top and the bottom. And here we did it at two different positions, at x equals 12 and x equals 30. Reason is this 30 has a maximum moment, and 12 is in the first section, is here at this point in here. And then we found maximum tension is 5,300 psi, like 5 ksi, and the maximum compression is not minus 6 and 6.6 ksi. Then we didn't stop the story here. We have to calculate the V. The V is, once we find it, then we have to find Q for the area. So it's another property of the area. And Q depends on the position from the top to the bottom. Top is Q is equal to 0, and they accumulate it down. So this is this is along the neutral axis here, the V and Q, the Q. And then the tau will be VQ over IB. And then you combine them. This is a shear. So you might have like two different criteria. Here's the failure due to shear is one criterion. This is a failure due to, so it's basically the shear actually in this case. So in this case, for instance, if the beam is designed so that it has layers, like let's say you have some kind of layer here and a layer here, and they're fastened together, then the interest in shear failure is at the interface between layers, for example, if it is like a beam like that. Variation could be a composite beam, and a composite beam, we didn't really dwell much on it, but there's also kind of concern about shear failure composite beams. So it depends on how the question, you look at it carefully to see whether you want to have to address shear failure by itself or shear plus tension in the form of von Mises. Depends on the final answer. So to summarize, a beam type question tests us in terms of ability to calculate stresses, ability to identify what is the difference between shear and uniaxial parts of the stress, ability to apply failure theory at the end of the day. So that's this question. Next question, if you see here, we have a rectangular member OB, and it's like a rod that's a 1/4 of an inch thick plate, and is pinned to the ground here and supported by 1/2 inch diameter aluminum rod. So it's aluminum, the CB. And at the end of the 150, we have 150 pound forces applied at A. So it's kind of a question here about deflection. And the best way to calculate deflections is in something that has multi-connections like that, or even curved sections, is to use Castiglione's theorem. This is kind of the spirit of Castiglione's theorem. So in this case, we want to calculate the deflection at point B, not where the load is at point B. So if we go back in our memory, Castiglione means we go to the point that we need to calculate deflection, and we apply a force in the direction that we need to figure out where the deflection is going. For example, B is going to move downward and it's going to move also horizontal, because once 150 pushes down, then this tip is going to go into like in a little circle here. So part of it is going to go down, part of it is going to go horizontal, maybe inward. They don't want the inward motion. They want the vertical down motion. So once this is decided, then you put the Q in the inward, in the downward motion, like down, like that. It's fictitious force. And then you use Castiglione to determine the energy stored in the different members. So you have a section OA and O and AB, and then you have also this rod CB to consider. And Castiglione is you take the derivative of all of the elastic energy with respect to the force. In this case, the fictitious force is Q, and that gives you the deflection. So we have first every one of these problems starts with the statics. We determine the reaction at C, the reaction here, and then the reaction at C is 54. Then we add a Q because this is a fictitious Q. So there's a Q inside, like a 54 plus Q in here in this rod. 54 plus Q. So if we have now energy, the energy part of it is going to be axial, stored in this axial, and the other part is be bending here and bending here. So axial, bending, bending. So the axial, the energy for the when we take the derivative of the energy with respect to Q is FL over AE times dF by dQ. So the product in the bottom is A times E. And when we do the bending, the product in the bottom is E times I. And you have M squared. So you take the derivative of this, you have M squared over 2EI dx. Then you take the derivative with respect to the Q force to get the energy. So this is U1, and this is U2, and then it's U total. We can add them up, and then we can get delta at point A. This is delta at point A because they wanted actually, this question was a little bit tricky because we wanted to have the deflection at B and the deflection at A. So it turned out to be that at B, the energy doesn't have any force components other than Q. Like if you look at the energy is just dictated by Q. So they have the force here, and then when you take the force with respect to Q is 1. So it didn't depend on the applied force in here. And we got a deflection base, as you can see here. But the energy parts, this one and this one, OA and AB, are bending, so they depend on the force F squared And when you take the derivatives, you have to take it, and then you start remaining depending on the force F here. So as you increase F, you get higher deflection at that point. So this is a problem in deflection with Castiglione. The next problem is a problem similar to what we had in the midterm, and or a variant. And the problem states as follows: we have a rotating disc, and it has an inside diameter, outside diameter, and a thickness. So we have, this is like a disc, like a flywheel. And then we shrink fit it on a shaft. So once you shrink fit it on a shaft, so it has a designation like H7U6. So you have the interference from these designations from the tables that we have in the book. And then that determines everything. It determines all of the forces, stresses, everything else. This number here, H7U6. So the cascade of questions are like follows. What is the minimum and maximum diameters? Okay, that's geometry. I look up H6U7. I find the interference. I add, subtract, find the minimum, maximum, and then figure out, if the minimum of the flywheel inner diameter is less than the maximum of the shaft diameter. Then that gives me the worst case scenario, which is the highest interference, and that I can translate to some force system. So that's what's the B is minimum maximum value interference. I think similar to midterm. Once this is determined, then we determine the pressure at the interface, equivalent pressure, and the equivalent pressure then determines the force, the stresses, because equivalent pressure will be contracting on the inner shaft, so it's under compressive pressure. But on the flywheel itself or the disc, it will be trying to expand it. So it'll be like a circular cylinder under internal pressure. And we have actually the formulas to work on that, and to determine, the stress values. We can determine radial and hoop stresses at the interface, and the factor of safety, and using distortion energy. And then we determine the horsepower transmitted and the torque. All of these come from that internal pressure at the interface. So these are this is the geometry calculations for the diameters, maximum, minimum, interface, and then once we have the pressure, depends on the maximum interference. The shaft material is the same. Then we have the pressure 20 KSI. Then that determines the stresses. We have radial and tangential stress on the shaft and on the disc. And therefore, we can use von Mises equivalent stress, and that gives us factors of safety. And that's it. So, okay. So this is for the stress. And then sometimes we ask questions about how much force is friction between the shaft and the disc. So it's a friction coefficient times the normal force. The normal force is the pressure times the area. And then what is the torque required? That's the force times the radius. So these are kind of design constraints that tells us how much torque it can support, how much horsepower can transmit the maximum. Okay, so I'll just take just a 5-minute break, and then I'll come back in a couple of minutes to continue. So if you just wait for a few minutes, I'll be back. Okay. Hello? Okay, so I'm back here. All right. Shall I continue? Okay, so for this problem, this is a gear train problem similar to one part of the case study. And we have a compound reverted gear train. Reverted means that the axis of the input shaft is in line with the axis of the output shaft. Puts a constraint on the sizes. And it's to be designed. Input speed is 150, output is 8400 exactly.
Professor, you're not sharing your screen.
Oh, I'm not sure. Oh, so, okay. Let me try to do it then. Okay. So the input is 150 RPM, output is 8400. So we know now the gear ratio. And if you divide these two, it gives us 56:1. So we need to increase the speed by 56 times, meaning that the input size of the gear is going to be very large and the output is going to be very small. So if it is like one step, so that's too drastic. So we take it in two stages. So we would have, if we take the square root of 56, is going to be 7 and something. So we might as well just make one stage 8, one stage 7. That's what we did. N2 over N3, 8, N4 over N5 is 7. So that's kind of two. We have 4 numbers to determine, 2, 3, 4, 5. So these are 4 numbers to figure out. And these are 2 equations. So the next equation is that if it is reverted, it means that the number of the diameters, the sum of the 2 diameters of the input should be the sum of the 2 diameters of the output, which means that the number of teeth when you sum the input should be equal to the output. So it gives us 3 equations and 4 unknowns. Cannot be solved. So we have freedom. We have 1 extra degree of freedom in this problem. So we have the extra degrees of freedom. Of course, we can just go ahead and use the constraint that we don't want an interference. So the minimum number of teeth will be 16, but we're not sure because it could be 17 or 18 or 19. It depends on how the numbers are going to work out. So in order for us to just make sure, then we take one of the gears, the smallest one, N3, for example, to be 1, just a reference. And then we ratio everything to 1. So N2 would be equal to 8 times N1, be 8. And N2 plus N3 would be 9, N4 plus N5. And therefore, we have now all of the gears determined if it were N3 equals 1. So N2 would be 8, and N4 would be 7 times N5, and N5 is 9 over 8. So now going backwards, we know that we don't want to have any gear that is fractional. So in order for us to make N5 to be not fractional, then the minimum with multiplier would be 8. So if you multiply everything by 8, that's going to give us N5 to be integer. So if we multiply everything by 8, it turns out to be that N3 would become 8 teeth. But 8 teeth is going to cause interference for sure, because we have a formula for the interference that N3 minimum should be 16.2. And therefore, we figure, okay, let's now forget about this 8 multiplier here and choose N3 equals 17. And then we cascade everything from there. and calculate N2 and N4 and N5 based on the fact that 17. So the exercise that you see here, we were trying to get some number that's integer, and we found that to be the N3 equals 8. If it came to be 80, for example, then there would be no problem because it would satisfy the interference requirement, but it came to be 8. So we kind of scratched our head, said, is 8 too small? Then we have to check the interference and found that actually 8 is too small. We need 17. So now we forget about 8 and go with the 17 and then use this multiplication as a multiplier, get all of the number of teeth here, 192, 24, 189, and 27. And then we sized, everything. And the efficiency of transmission is 75%, which means that the output horsepower is not exactly equal to the input horsepower, it's 3/4 of the input. So it gives us 0.75 of the input, T2 omega 2 is equal to the output T5 omega 5. And that, knowing the horsepower, which is 1.5 horsepower in this problem, like it's given here, 1.5 horsepower, then we can determine the torques. So we can determine the torque, T2, and T5, the output torque. So this is part of a problem because you can go ahead and now design many things as we've seen, but it gives you a glimpse of what can be done mixing considerations of gear layout, shaft layout, and horsepower, torque, force requirements. The last problem here is a fatigue problem. And the fatigue, we do not have many systems that are in this course that have fluctuating stresses other than the shafts. So it ends up always designing shafts. So a shaft will be here. You have a shaft that has small diameter, and then you have two gears, one in A and one in B. So I have shoulders, you have keyways, and then the inner part of the shaft is larger. And we want to determine radial tangential components of the gear forces and fatigue factor of safety. So this is a section of the problem that I described earlier as a full design of a gearbox. So this is just one part of it, which is a shaft design. And this part here is what do we need to know is we want to know the transmitted horsepower, the transmitted power is 30 kilowatt power, and the RPM. So from these two numbers, we should be able to figure out the forces, determine the moments. From the moments, we can, and the torque, we can determine the stresses, and then we can decide failure. So here's, this is what we compute the velocity, the pitch line velocity, pi dn down here. And if we multiply this by the force, tangential force, it gives us the horsepower with the conversion factor. And then we use the tangent to convert tangential to radial. So we have tangential force, radial force for gear A and gear B. And exactly very similar to the gearbox design problem that I reviewed. So you have the force system concentrated. You have two planes. You have X, Y, and Y, Z. And you have moments, and you have to figure out what is the maximum location of maximum moment, take the square root of those, and then also define the torque. And from these two, you can find the stresses. And then you have all kinds of factors here for stress concentration at the shoulders and the end mills and so forth. So that gives you kind of a flavor of the types of problems. They can see they're not so difficult, but they need some kind of practice because you have limited time. And to get it accurate, you just have to practice and also use common sense. If the numbers don't work out, you probably can estimate it or just leave it as an estimate, like estimated this by this number and this number, so you don't get bogged down by a lot of details. So I think this is all what I have for review, and I wonder if you guys have any questions or anything that needs clarifications.
Would you be willing to post this exam as well, so we can use it to practice?
Yeah, sure. I posted last summer's final solutions, and I'll post the fall 14 final solutions as well.
Fantastic. That will be very helpful.
Yeah. Any other questions?
I have a quick question about the comprehensive question.
Yeah.
So is that going to be given to us like right after the final, or how does that work?
Yeah, if you are taking the comprehensive, you just have to send me an email when you're ready, and it's going to be a 24-hour take-home question, and it would be the name of the exam is comprehensive, meaning that's combine many things together. So it will be a design problem from what you've learned in class, but it will be kind of touching base on many things.
Okay.
Yeah, and then once I get the email, then I send you the question, and within 24 hours, you can send it back to me.
Okay, kind of like just upload our work in a PDF or something.
Yeah, you can like do your work and scan it, put it in PDF, and then you can send it to me as an attachment.
Okay.
Yeah.
Thanks.
Now, what's the time frame on that? Is that from now until Friday and now until Saturday, or
For the comprehensive?
Correct.
Yeah, for the comprehensive, it would be after the final. Like the final is Saturday the 29th, and then we have another week. Within that next week, you can request a comprehensive.
Okay, thank you.
Time, yeah, just whenever you're ready. Because after the exam, you probably have more time to study or to organize your thoughts, and then you'll be ready for a kind of a long night of calculations on a comprehensive question. Okay. All right. I think this is good, and I wish you all good luck on the final. And if you have any questions on the, you can send me email. Also, you can use the TA. UA is very helpful with the solutions, and he has a lot of knowledge on COMSOL and Abacus, and to finish your final report. Okay. All right. So goodbye, and then we'll see you later.
Thank you.
Okay. Bye-bye.